written in terms of this approximate T guys. And then the last base here, which is called as exchange correlation energy, which is the difference between exact ground state energy density minus these approximate forms of Hartree and the single particle kinetic energy. So it's this functional form which is not known to us. So what was achieved with this simple approximation or simplification? Earlier we did not know the form of this and this. Now we know the form of these three terms, but we have absorbed all the unknowns of DFT in this single exchange correlation energy functional. And that is where much of the approximations of DFT come in. Until this point, it is exact. It should apply to all fermionic electronic systems. So what is the approximation? Effectively, basically, you end up in a Schrodinger-like equation, which are called as Kohn-Sham wave equations, where you have kinetic energy, external potential, the Hartree potential, and this is the unknown part, which is exchange correlation energy. So how does one tackle this? Basically, you approximate a many-body problem by an effective one-body problem, which albeit is non-linear, where instead of each electrons here, you say we will look at each electron as an individual particle, which is filling the external potential coming from the rest of the electrons, and that's what is captured in this three terms. And this exchange correlation energy is now approximated using what is called as local density approximation. And the y-axis is rho as a function of position. And suppose you want to know what is the exchange correlation energy at this point, you look at the density here, and then you look at the homogeneous electron gas exchange correlation energy, and that's what is approximated. So what this means is you have a very complicated inhomogeneous electron gas, and locally you think of it as a homogeneous electron gas and get the exchange correlation energy from that. Okay? So most of the equations are over on this slide. Sorry for having this in this general talk, but I hope it gives you an idea what DFT is and where its approximations and limitations come from, and it's in this exchange correlation energy. Okay, so in the last year, we actually very important captures the energies of various types of chemical bonds, starting from hydrogen bond of a milli eV strength to ionic and covalent bonds which run into 10 eV of scale. Okay? So this is sort of a very recent new development density functional theory, and what we accomplish using this is shown here. Basically, for weakly bonded systems like water clusters, we get the accuracy which is comparable to quantum Monte Carlo or couple cluster approximation here using this new functional, whereas the standard DFT was giving totally wrong results. Second is the covalently bonded system, silicon metallic versus semiconducting form of silicon. And again, you see the new functional form gives you exact energies as diffusion Monte Carlo results. So whereas the standard earlier versions were quite wrong. And these are oxides, which are third class of materials, where also the bond lengths are given more or less exactly using this new density functional. Okay? So indeed, this is a very big improvement in over what was known in what was used in density functional theory before. There was a News and Views article by Roberto Carr on this paper, which says it's fixing Jacob's ladder in the sense if you want a method which is super accurate, which works for all types of problems, heavenly method, well, this is sort of the various approximations that you go through. LDA, what I told you, is sort of the lowest level of approximation. And what we introduced here is this hybrid functional, scan functional, which gives you accuracy of a non-local method at the cost of semi-local method. Okay? So we are hoping that this will change the way DFT is applied to fairly challenging wide range of problems. And of course, the codes which we use for these calculations are all open source code. They are problems can be tackled using these computer programs, using the softwares with fairly moderate computing resources. You can for the new functional. Yeah, unfortunately, some of them are lagging behind to implement the new functional, but I'm sure it will get in there very soon. Yeah. Okay, so what do we learn from DFT calculations, which connects with, yes? Yeah.
Presumably you're doing a derivative expansion. You're putting in that in and then netting it.
Yeah. No, that was, okay, good question. So let me go back to that picture. So that expansion corresponds to basically GGA, generalized gradient approximation, and that doesn't do much improvement actually. Why this method is so good, I didn't go into details of it, is it satisfies 17 sum rules which are satisfied by the exact solution of the No, it's not an expansion. It has that functional form that I showed you, and it is supposed to satisfy the 17 sum rules, and that's why it's doing reasonably well. I'm sure there is still a way to improve it, but that's where we are today. Okay. So what do we learn from DFT calculations? And by the way, as I mentioned in my abstract, this is what is considered as the standard model for materials, which basically uses no empirical information in description of a material. And remember, properties of a material are essentially related to derivatives. So if you can calculate that energy effectively, you can get most of the properties out. And let me now show you the 3 levels of structure that we get from this calculation. First step is basically the atomic or geometric structure, where if you minimize the total energy that I defined, you can easily get the atomic structure, which gives you coordination number and variety of symmetry properties of it. If you want to use X-rays experiment, you would have to use X-ray diffraction to get this type of structure, whereas our calculations give this kind of information simply through minimization of energy. Second level of structure, I call it dynamical structure, or what is called as phonon structure. It says how atoms are organized or oscillating time around their as a function of wave vector. These are acoustic phonons, which give you how stiff is your solid, and these are optical modes, which give you coupling with IR or visible radiation. And when you use Raman or IR spectroscopies, you basically get phonons only at these few points, okay? Whereas if you want to get the full dispersion using experiment, you really have to use what is called as inelastic neutron scattering. Whereas these calculations can fairly accurately give phonon dispersion even on a laptop in a matter of a day from simple materials. Okay, so they are quite powerful and useful. The third level of structure is electronic structure, which people often call as band structure. And this is one place where I should clarify that DFT methods are not band structure methods. Electronic structure come out as a byproduct of a DFT calculation. The main target and success of a DFT is actually the total energy function, which is what I have emphasized so far. Okay. So band structure, of course, is very useful, but quantitatively it's often wrong. The band gaps are underestimated, and sometimes you get a wrong metallic ground state for systems which are insulating. So there are ways to improve that. Of course, experimentally you can use electron spectroscopies to get these kind of pictures, where this is a direct outcome of a DFT calculation. Okay. So now I'm going to, this was sort of introduction to the methodology. If there are any questions, I'll be happy to stop briefly and take them.
So why is the electronic structure sometimes predicted wrongly?
Okay. So as I introduced DFT, Pratap, it's a theory for quantum ground state of many electrons. It does not include electronic excitations at all. So it's not supposed to be correct. Then you will ask, why is this correct in the first place then? Of course, you'll see thousands of papers which quote this type of band structure and talk about it, discuss it in the paper. The reason is the mathematical structure of the Kohn-Sham equation is quite similar to Schrodinger equation, and the potential is very realistically derived. So it does have a roughly correct curvatures and structure. But quantitatively, band structure is not something I would ever trust coming out of a DFT calculation. Yeah.
Question was about electron and coordination.
Yeah.
How electron coordination in DFT, and can you manipulate it or change it and that's change the band gap, or
Yeah.
like you get it out of the you take a structure and you get the resulting electron coordination.
Okay. So as I described, DFT is a parameter-free theory. So there is no fixing parameter one can use to get the band gap right. But your suggestion is good. There are people who have developed what is called as hybrid functional approaches. What they do is they observe the fact that if you use Hartree-Fock calculations treat exchange interaction exactly, it gives you overestimation of band gap. And DFT typically gives you underestimation of band gap. So hybrid functional try to mix exact exchange and DFT LDA with certain proportion, say 0.3, and then they get band gaps which are very close to experiment for a wide number of compounds. So that is done, but that's not something which is a rigorously founded approach to getting band structure. Yeah. Yeah, at the moment, this is a zero temperature theory, and as I explained on the earlier slide, to get final temperature properties, you would have to use statistical mechanics. As shown here, this is the Hamiltonian of, sorry. Yeah. So this is the Hamiltonian of collection of atoms. You can use it in Monte Carlo simulations or molecular dynamics to get final temperature properties. So, but the same functional result. As I will show, I will be using that temperature. Any other theories? No. So most of the simulations I will talk about, they involve mainly phonons, and they are obtained within the Born-Oppenheimer approximation. Yeah. So temperature strictly applies to phonons, not to electrons in that case. Okay, so first topic is ferroelectric oxides, and I will quickly go through it. Ferroelectric oxides occur in this cubic perovskite structure, AbO3 compound like barium titanate. Titanium is at the center of this oxygen octahedron. At high temperature, it's a beautiful cubic structure which is centrosymmetric. As you lower the temperature, it becomes ferroelectric, which is coming because this central titanium atom gets off-centered at that transition temperature, giving you a finite electric dipole moment in the low temperature phase by breaking inversion symmetry and also distorting the lattice along C by A ratio. So once a phase transition occurs and symmetry is lowered, it gives rise to new functionality in the material. Okay, this is an interesting simple message I want you to take home. So this is a breaking of inversion symmetry at the phase transition, and that's what is responsible for the linear piezoelectric property of this material. This property vanishes identically to zero in the high temperature phase. And that's because just simple symmetry argument that you need a broken inversion symmetry to have linear piezoelectric response. Secondly, this titanium off-centered, you can flick to the opposite side by applying negative electric field. And as a result, you get polarization electric hysteresis loop, which is a nonlinear property which can be useful in making computer memories, particularly non-volatile computer memories which retain memory even if you switch off the power. Okay? So the fundamental message here is phase transitions govern the functional properties relevant to applications, similar to magnet. Okay. So our question now is what happens to these phase transitions, which are very fundamental to functionality of a material, when you have that material in the thin film form, which is what is typically used in technological applications. So of course, it's a finite temperature phase transition, as Sri Ganesh asked, and usually we would typically use molecular dynamics or Monte Carlo simulations. Direct DFT simulations are very expensive. not talk about this, so I won't go into detail. We can go to second round of code tuning in real space, and that gives us the Windberg theory, and that allows you to access lots of longer length. So the first part, molecular dynamics, we have our own open source software called FAIRAM code, molecular dynamics, developed by my ex-postdoc Takeshi Nishimatsu. And this code is very useful for doing MD for large scale simulations of ferroelectric oscillators. It's called mixed phase molecular dynamics, means there are infinite range interactions which are treated in reciprocal space, so it's very efficient in that. So using that code, we can directly predict the phase transitions in variant dynamics, and you can see the TCs are about 25% underestimated with respect to experiment. This is with the LDA, by the way. I'm not showing you the results which we obtained with the new functional that I showed. The results are significantly improved with the new functional which we have. Likewise, for lead titanate, we get a TC of about 660 Kelvin, whereas experimental TC is about 760 Kelvin. Okay, so it's a fairly good accuracy that we can predict phase transitions quantitatively and in a material specific manner. But our main goal is how do these phase transitions transform to nanoscale thin films of ferroelectrics. So what we want to simulate is a typical experimental